Hi, everyone. This is going to be a lesson about antiderivatives for Calculus 1. And yeah, antiderivatives are the beginning of a new topic for us. So we're going to be talking about antiderivatives and also this thing called the integral. And really, this is the topic that we're going to be talking about for the rest of the semester. So this lesson will kind of introduce the topic, and we'll see some new kinds of problems that we can solve. So we already know all about the derivative, so let's talk about what is the antiderivative. All right, so this is going to be antiderivatives, and I'd like to start by telling you what is our motivation to discuss this topic. And the basic idea is, what if we know f prime of x and want to know f of x? So that's an interesting question because we haven't really done it in this direction this semester, right? Usually we know f of x and we try to find f prime, but what if we know f prime and we'd like to know what was the original function f of x that gave us that f prime? And we've seen applications of the derivative this semester, so maybe we can do some of those applications but in reverse. For example, if we know velocity and want to know distance. You remember a long time ago we talked about distance, velocity, and acceleration, and how you would go from a function to its derivative in order to get velocity. And then you would take the derivative again if you wanted acceleration. But what if you want to go in the opposite direction? What if you know velocity and the question is, what is the distance? You would need something that's sort of the opposite of the derivative. You'd need to go from f prime to f. Here, let's look at a little example question. Let's say we're given, let's see, which one do we want to do here? Let's say we're given f prime of x equals 2x, and I say I would like us to find f of x. Well, the answer is not 2 because, 2 would be f prime prime. It would be the second derivative. So we don't want to do that. We don't want to take the derivative of this. We want to think the other way around. So it's sort of like, well, what function would have this as its derivative? How about this? You could probably think of a function that has this as its derivative. We could do, we know that the derivative of x squared equals 2x. So f of x equals x squared. How about that? So f of x equals x squared works because if you tried to find f prime, you would get 2x, and then that means that this is the answer. Well, how did we get that answer? It was like we kind of thought about what we know about derivatives in reverse. I was thinking, do I know a function that when I take the derivative of it, I'm going to get 2x as the result? And x squared seems like a good choice. But is that the only answer? Do you think that's the only answer? Well, it turns out that this also works. X squared plus 5. Because the derivative of x squared plus 5 is 2x. Also, what if I did f of x equals x squared plus 6? That works. The derivative of that is 2x. So it seems like I could do plus 5, plus 6, plus 7, plus a million. I could do plus 1. I could do minus 1. I could do minus 100. So it seems like there are a lot of possible answers to this. All right, so there's more than one possible answer. I think that the answer of f of x equals x squared seemed like the most natural choice, but technically, any of those other ones are also good. So it seems like we could add a constant, like x squared plus a constant seems like it would work because the derivative of a constant is 0. Do you think there's anything else you can add besides a constant? Do you think you could like multiply this by something or, divide it by something? Would that still work? We're going to talk about that soon. We're going to talk about it soon. First, I have to give you a definition. I said that we are kind of thinking about the derivative, but in reverse, and we have a name for this. A function capital F is called an antiderivative of lowercase f on an interval I if capital F prime of x equals lowercase f of x for all x in I. And I'll just say right now, note, we often have the interval being negative infinity to infinity, and that's often kind of assumed. So we're not always going to specify an interval that we're working on. Often it's going to be all real numbers, or it might be the domain of a function. But the main thing I want you to take away from this is that capital F is an antiderivative if capital F prime equals lowercase f of x. In our example above, we could do capital F of x and say x squared is an antiderivative of lowercase f of x equals 2x. So I'm using different notation than what I did above. I'm switching to this kind of capital F lowercase f idea that the definition uses. This is an antiderivative of this because capital F prime equals lowercase f of x. Makes sense, right? We also found other antiderivatives. We also found, x squared plus 5 is an antiderivative of 2x. X squared plus 6 is an antiderivative of 2x. So that's why we say it's an antiderivative. We don't say it is the antiderivative because it seems like there's going to be more than one answer. So we say this is an antiderivative. Oh, actually, I left out that word. I meant to say an antiderivative. But yeah, there you go. Let's look at another example. In fact, the above example was phrased just with lowercase f, but let's do an example where we use this capital F and lowercase f. So how about if lowercase f of x equals x squared, find an antiderivative of lowercase f. I'd like you to think about this. The answer that we write should be sort of a capital F of x. I'd like you to maybe pause the video if you'd like and think about this for a minute. All right, so here's the idea. We want a function that when we take the derivative of it, the result is x squared. So what goes here? That's what we're trying to figure out. So this is a little bit harder than that first question, right? Do I know a function that when I take the derivative of it, I get x squared? All right, so how about this? Here's an idea. What if I did x cubed? Does that work? We're just trying this out. We're not sure if that's the answer yet. But I know that when you take the derivative of x cubed, the power reduces by 1, right? So I guess you get 3x squared. So this is almost what we want. Really, I want something that when I take the derivative of it, I get just x squared. This has a 3 out front, so this can't be the right answer, but it somehow feels close. It's 3 times bigger than it should be. It's 3 times bigger than it should be. So here's an idea. What if I did 1/3 of this? This works, doesn't it? That gets you x squared. So we could say capital F of x equals 1/3 x cubed is an antiderivative of f of x equals x squared. And that's a good answer. I don't think it's the only answer, but I do think that this is probably the simplest answer. Because also, you could take this and add something to it, and it would still work, right? This works. Minus, I don't know, 23 works. So just like with the previous problem, it seems like we could add or subtract any constant and still have an antiderivative. Because, when I do d dx of this is going to be x squared. d dx of this is going to be x squared. So all of these work as antiderivatives. Now we have a theorem that's going to explain this. It says, if capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of lowercase f on I is capital F of x plus capital C where capital C is an arbitrary constant. So this theorem is kind of officially stating what I think we've started to observe above, which is when you find an antiderivative, you can add any constant to it and it still works. And the constant could be positive or negative, because it just says an arbitrary constant. It doesn't say that it's necessarily positive. So this could be, plus negative 23. C could also be 0, because 0 is also a constant. So really, when we say an arbitrary constant, we're saying you could add anything as long as it's not, you know, a function of x or something like that. You have to be adding just a constant. Like you can't add 7x. That would not get you the same derivative, but you can add 7. Furthermore, so this theorem is saying that you can add any constant, but it's also kind of telling us, it's saying that's the most general antiderivative. So it's basically saying that that's all you're allowed to do. You're only allowed to like add constants. Well, that's good because it means that even though there are lots of different answers, I mean, you could say there are infinitely many answers, right? Because you could add any constant, any real number that you could think of. So there's infinitely many answers, but this theorem is telling us that the answers can still be kind of summarized as like a family of answers. The most general antiderivative, in this case, it would be 1/3 x cubed plus any constant. Here, let's do another one. Let's say that we want to find the most general antiderivative. I'll do this one for us. Find the most general antiderivative of lowercase f of x equals secant squared x. So I'm thinking about trig functions. I'm thinking about trig function derivative rules that I know. I know the derivative of sine. I know the derivative of cosine. I know the derivative of tangent. Yeah, actually, we know the derivative rule for tangent. Do you remember that? Derivative rule for tangent is secant squared x. So one particular antiderivative is capital F of x equals tangent x. This is one antiderivative of lowercase f. Therefore, in general, the most general antiderivative would be tangent x plus c. And that's what this problem was looking for. And I need to tell you that in this context, when we write an answer like this, it is understood that c is used to represent an arbitrary constant. So we don't have to say tangent plus 7, tangent plus 8, tangent plus 9. We just say tangent x plus c, and from the context and from just sort of the standard notation that we write this in, we understand that the plus c means tangent x plus any real number. So it's kind of more interesting for problems to ask us this type of question, you know, to ask us to find the most general antiderivative, because that way we have found all answers. Like this sort of summarizes all of the antiderivatives of this function. It's always tangent plus a constant. Now we understand that the reason why you're allowed to add a constant is because if I did d dx of this, like what if I had a constant in here, you know, plus 17? If you take the derivative of a constant, you get 0. So that's basically why it's okay to do that. You could also sort of try to visualize this, like if you have a function and you add a constant to it, all you've really done to the graph by adding a constant is you've shifted the graph vertically. You know, you've shifted it upward if c is positive, or you've shifted it downward if c is negative. Well, when you shift a graph up or down, it doesn't change the derivative. It doesn't change the slope of the tangent line. So that's another way to think of it. That's why it's okay to add a constant. Let's do some more problems. So I did that problem for us by thinking about secant squared and, do I know a function that when I take the derivative of it, that's what I get. I'm going to ask you to do a few like this. Find the most general antiderivative of, I'm going to give you 4 of these. Now, because it says the most general antiderivative, I think the answers we find are going to be something plus c. So keep that in mind. I'm going to give you 4 functions. F of x equals x cubed. F of x equals, let's do sine of x. F of x equals cosine x. And f of x equals e to the x. So I'd like you to pause the video and try these 4. All right, so we've got kind of an assortment of functions here. We have some trig functions. We've got an exponential. The first one is x cubed. Earlier, we talked about x squared, so I think that's a good one to start with, is this x cubed problem. So I guess I'm going to kind of write my thought process for part A. We notice that the derivative of x to the 4th is 4x cubed, and that's almost what we want. Right, I want something that when I take the derivative of it, I get x cubed, and this has a 4 out front, so this is 4 times bigger than it should be. So instead, let's try 1/4 of it. The thing I got was 4 times too big, so I'm going to try 1/4 of it. And yes, that does work. So if we want to write the most we just found a particular antiderivative of it. We found that, 1/4 x to the 4th is an antiderivative. But the most general one would be capital F of x equals 1/4 x to the 4th plus c. And we need the plus c. That way the answer we're giving is the most general antiderivative, not just one antiderivative. This sort of summarizes all of the antiderivatives for this function. All right, I think I need to move the top page out of the way, so we're gonna lose the questions, but I think you probably have them in your notes by now. For part B, I'm thinking I want the derivative of something equals sine x. And we're trying to figure out what has to go here. Well, I know the derivative of cosine is negative sine. That's almost what we want. How about you try negative cosine x? That works. So the most general antiderivative would be negative cosine x plus c. For part C, we want something that when we take the derivative of it, the result is cosine. And we're figuring out, well, what needs to go where this question mark is? Sine x works. Yeah, that works. So then the most general antiderivative would be the particular antiderivative that we found, but then with a plus c attached to it, because you could add any constant you want. And finally, the derivative of something that needs to equal e to the x. And we remember that e to the x is its own derivative. So I guess you could say e to the x is its own antiderivative also, but we need the plus c in order to be giving the most general antiderivative. So these answers, because they have plus c attached to them, and it's understood that that represents adding any real number, it's like a family of solutions, a family of answers. Every antiderivative of e to the x is in the form e to the x plus a constant. Constant could be 0, could be 1,000,000. This answer covers all possibilities. Now, I think all four of these, we kind of got to these by thinking about derivative rules, right? And we were like, oh, we need something that when I take the derivative of it, I get this as the result. And that's a good way to think of these for now as we're starting to learn about them. But really, we would like to establish some rules and patterns so that we don't have to do every one from scratch. We'd like some general rules. So here's a question. What is the most general antiderivative of f of x equals x to the n, where n is a positive constant? Now, we've already done this for 2 and 3, so let's talk about this together. We've said how do we want to write this? For f of x equals x squared, we used this, right? And for f of x equals x cubed, we just found 1/4 x to the 4th plus c. So do you see the pattern here for x to the n? What do you think is going to work? Look at where the 3 and the 4 wound up. Do you think we can just do 1 over n? It says n is positive, so we don't have to worry about dividing by it. Well, actually, it's not 1 over n, is it? I guess the 3 turned into a 4, so it's kind of like n needs to turn into n plus 1. Let's try this. 1 over n plus 1, x to the n plus 1. Does that work with the plus c? Let's check this. Let's check. If I take the derivative of this, what do I get? Remember, n is a constant. We don't need to do any kind of product rule or quotient rule or anything like that. N is a constant. We just think of it like a number. So we have a power up here. It's going to come down out front. It's going to get multiplied by the 1 over n plus 1 that's already there. The new exponent is going to decrease by 1 when you have an exponent of n plus 1 and you decrease it by 1. Yeah, this works out. So what we can say then, the most general, we're going to state this as an official rule. The most general antiderivative for f of x equals x to the n is, I'm going to write it slightly differently. It's the thing that we found here, but the way that we usually write it is x to the n plus 1 over n plus 1. That's the same thing I wrote above. It's just we put the n plus 1 on the bottom. That's just usually how this is written. Now, when I asked, when I posed this question above, I said where n is a positive constant. And you might say, like, does it still work if n is negative? And in fact, this works for any n except there's one value of n where this rule doesn't work. What value of n do you think that's going to be? Yeah, this does not work for n equals -1. Why -1? Because if we try to apply this rule with n equals -1, we'd be dividing by 0. So that doesn't seem right. So it does work for any other constant n. Because with any other constant n, we're not dividing by 0. Everything is fine. So I don't know. We could do a quick example. Like if you've got a function and you want the most general antiderivative, applying this new rule that we have, I guess if the function is f of x equals x cubed, we've said that the most general antiderivative is x to the 4th over 4 plus c. Do you see that that's the same thing that we wrote above? Here, what we wrote down here is the same as what we wrote up here. It just looks a little different because instead of having a 1/4 in front, we put it over 4. It's the same thing. What if I asked you this for x to the 9? You could use this rule. You add 1 to 9, right? So it would be x to the 10 over 10 plus c. What if you had x to the -5? I mean, I said that this rule works for any value of n except for -1. So yeah, this should work here for -5. So it's going to be x raised to the, what exponent do we need? I guess if n is -5, then we need to increase -5 by 1. -5 plus 1 is -4. And then we also divide by that new exponent. Do you think maybe we could write this a little differently? That's kind of, I mean, I guess that's fine the way it is. I guess if the question was phrased as x to the -5, I guess what we wrote here is okay. But another way to write it is we could say -1 over 4x to the 4 plus c. Something like that if you want. All right, I've removed the rule, but I think you've got it in your notes by now. How about x to the 1/2? Oh, by the way, x to the 1/2, isn't this the same as the square root of x? Yeah, so we're saying what is the most general antiderivative of the square root of x? I probably should have just saved this to be a problem later, but let's talk about it now. Well, we could try to apply this rule. So we need x raised to a power, and then we're going to be dividing by something, and we're going to have a plus c. So what needs to go here? If n is 1/2 and we want to do n plus 1, what happens when you add 1 to 1/2? You get 3/2. But this is a little messy because look at that. The denominator is itself a fraction. And you know I don't like having a fraction inside a fraction. So we can fix this up a little bit. A good way to fix this up is instead of dividing by 3/2, let's multiply by the reciprocal. All right. So there you go. We just did a little table of a bunch of little problems. So the most general antiderivative of the square root of x, also known as x to the 1/2, is 2/3 x to the 3/2 plus c. And you don't have to memorize that as like a rule for the square root function. What you should probably memorize is this thing that we put a box around. This is a good formula to know. So we just used it on 4 little problems. And I said at the top of the screen here that this works for every value of n except for -1. So what about f of x equals x to the n when n equals -1? X to the -1 is also known as 1 over x. So this is really asking us what is the most general antiderivative for f of x equals 1 over x. I think we know one antiderivative for it. Here's a guess. Here's a guess. Do you remember the derivative? Something that when you take the derivative of it, you get 1 over x? ln of x. ln of x. Yeah, if you take the derivative of ln x, you do get 1 over x. There's one issue with this. There's a reason why I'm not putting box around this yet. The issue is that these two functions aren't defined on the same interval. You know how earlier we were talking about like the interval capital I, and I think I said usually we're not going to have to worry about that so much. Well, this is one case where it actually is a slight issue. We would like these to have the same domain, really. It would be better if we had a most general antiderivative that had the same domain as the original function, because 1 over x is a function that is allowed to have negative x values, but ln x is not. ln x is not allowed to have negative x values. So we can do better. We can do better. Oh, by the way, if we said that we just wanted an antiderivative on the interval of positive numbers, then this would be fine. But we didn't really say it, but it's kind of preferred for us to find one that's on the entire domain. Okay, so I'll tell you the rule. And it's going to be a slightly modified version of this capital F. Rule: the most general antiderivative of 1 over x is How are we going to fix this issue with negative numbers? Well, we actually just put absolute value around it, and that takes care of the issue for us. Yeah, so this is the only function where that's kind of an issue, or at least it's the only function that we're going to look at in this class where that's an issue. Now we have lowercase f of x and capital F of x have the same domain, which is all real numbers except for 0. So I'll just say one sentence, because capital F of x and lowercase f of x have the same domain. And capital F prime of x equals lowercase f of x for any x in the domain. So that's why this is the rule that we use. This is kind of the preferred form. The absolute value takes care of any negative numbers by making them positive. Seems like a neat little trick, but we only really use it this one time, just for this rule. So you can see that we're starting to establish some rules. I mean, we know how to find antiderivatives. It seems like x raised to a power, 1 over x. One case of this that we did was the square root of x. We've also looked at sine and cosine and e to the x. Let me tell you some other rules. First of all, if capital F of x is an antiderivative of lowercase f of x, then a times f of x is an antiderivative of a times lowercase f of x for any constant a. Ultimately, what that sentence is telling us is that constants sort of behave the way that we would expect them to behave. And one other rule, if capital F of x and capital G of x are antiderivatives of lowercase f of x and lowercase g of x, respectively, then capital F plus capital G is an antiderivative of lowercase f of x plus lowercase g of x. Let me move this and give you a chance to see that. This is a g over here. G. So this is just saying that sums of functions basically work the way that we would expect them to work. And in fact, this also works for subtraction. I'm not going to write that out as a separate rule because subtraction is just adding a negative quantity. So if we have a rule like this with a plus sign, you could just say, well, you know, g of x might be a function with a minus sign out front. That's okay. What I'm saying is that this works with a plus sign and with a minus sign. I'll show you how these rules help us to solve some problems that we wouldn't be able to do otherwise. Let's find the most general antiderivative. You know what I want to say right now? Hang on, before I write this problem. Find the most general antiderivative of... Doesn't this seem like really tedious to write this every single time. Find the most general antiderivative of. Wouldn't it be really nice if we had like an abbreviation for this, or maybe even like a symbol to represent this phrase? So that's coming soon. We're gonna have a much shorter way of saying this. Find the most general antiderivative of. That's coming in a few minutes. But for now, the function I'm going to give us, I'll do this problem for us because this problem might look intimidating at first. It seems like a big jump in difficulty, but it's not so bad. We can do this. Like all of a sudden we went from dealing with problems like x to the third or x to the fourth, and now I'm giving us something like this. All right, we can do this. So here's my idea. Before I find the antiderivative or an antiderivative of it, I'm going to rewrite this function in a different way. You know that sometimes in math it helps to rewrite the problem in a different way. And that fraction, that something over something, I'm going to split that up. I'm going to write it as 2x to the fifth over x minus, we said earlier the square root of x is the same as x to the 1/2. So let's do that. X to the 1/2 over x. The reason why I split this up is because we can now use some rules about exponents to write this in another way. We could say 4 sine x plus 2x to the fourth. See what I did there? X to the fifth over x. And then what do we do for this one? Minus x to the 1/2 over x is x to the negative 1/2. So this is equal to the original function, but now if I try to find an antiderivative, I lost the word antiderivative. Sorry about that. Now if I try to find an antiderivative of this, it looks easier than the original problem. Capital F of x. Now I am finding an antiderivative of this. We said earlier that an antiderivative of sine x was negative cosine. So negative cosine x. The 4 is still there because of this fact that we said above. We said that, a times a function, a times a function. So the 4 just stays. The 2 is also just going to stay. 2 times, what is an antiderivative of x to the fourth? Well, x to the fifth over 5. Minus, what is an antiderivative of x to the negative 1/2? Apply that rule that we said earlier for x raised to a constant. This is going to be x to the 1/2 over 1/2. And plus c. So this is the answer, but I think I'm going to try to rewrite it a little bit nicer. Let's write it as negative 4 cosine x. How about plus 2/5 x to the fifth? And then we can fix this up, right? Instead of dividing by 1/2, let's multiply by 2. And instead of writing it as x to the 1/2, I'll write it as x square root for my final answer. And that is the most general antiderivative of lowercase f. By the way, you can check this answer if you want. If you want, I'm not going to do all these steps, but take the derivative of it. Take the derivative of the answer, and it should equal the original problem. It might look a little different, like it might be in a different form. It might not pop out exactly looking like that, but it would simplify to the same thing. So that's true for any of these types of problems. I want to talk a little bit more about this plus c that we've been adding. It seems like any problem that's phrased this way, find the most general antiderivative of a function, it seems like we always have a plus c in the answer. Let's talk about this. More about plus c. All right, so notice if I had lowercase f of x equals x squared, we would say the most general antiderivative of this would be capital F of x equals x cubed over 3 plus c. And what if I had g of x equals x cubed? We would say that the most general antiderivative is capital G equals x to the 4th over 4 plus c. Nothing that I've said so far should be surprising. I mean, this is kind of what we've been saying today. Now, we said an antiderivative for f of x plus g of x is capital F of x plus capital G of x. That was that fact that I said above. So do we just add these together then? Like if I wanted the most general antiderivative of lowercase f of x plus lowercase g of x, like x squared plus x cubed. If I wanted the most general antiderivative of that, should I just add these answers together? That would look like x cubed over 3 plus c plus x to the 4th over 4 plus c. I'm going to put a question mark next to this. It seems like it turned out a little bit weird because now we have a plus c and another plus c. And that's the part that I'm kind of questioning here. If we have plus c plus another c, couldn't we just combine those? Like, couldn't we just say plus 2c? Instead of adding, plus c, and it seems like with some problems, maybe you'd have like a plus c, plus c, plus c, like you'd have a bunch of them. Do you merge them together like this? Well, the answer is no. We just write x cubed over 3 plus x to the 4th over 4 plus c. You just write one copy of c. Now, this takes some getting used to. It might seem a little weird, like what happened to the other c? So let me explain this. Just writing plus c is good enough because of what c represents. C represents an arbitrary constant. When we wrote two of them here, really you could say that they might be different constants. Like this one up here might be a plus 5, and this one here might be a plus 7. So maybe instead of merging them together to 2c, maybe I should have thought of one of them as like c1 and the other is c2, because they might be different numbers. Maybe it's a plus 5 and a plus 7, but the point is we could just write it much simpler as plus 12. So no matter what these constants are, they're any real numbers, they can always be merged together into one real number. And in fact, it's preferred to write it this way because this is simpler. So we prefer to just write plus c once. Like I said, this might take a little time to get used to, but in these types of problems, if you have multiple plus c's, they just, in the end, you just have a plus c at the end. That's it. You could say that the other plus c's kind of got absorbed into this one. Just adding one arbitrary constant takes care of all possible real numbers that you could add. Okay, also another thing that I'm going to tell you is that it is okay to not write plus c when you're in the middle of solving a problem. Like when you still have simplifying steps that you need to do, you don't need to write plus c in the middle of a problem. Just make sure you have it at the end. You're going to see me do that for some problems. I'm not going to write plus c until the very end. Sometimes it's easier that way because then you don't have to deal with like a bunch of plus c's. Just put one in the final answer. Now, you only put a plus c if it's asking you for the most general antiderivative. If a problem says, like, specify one particular antiderivative, then I wouldn't put the plus c. All right, this all takes some getting used to, but we're going to do some more problems, and the more times we do problems, the more comfortable we'll get with all this. Okay, I have two problems I'd like you to try. Find the most general antiderivative of. Boy, I'm looking forward to when we have a way to abbreviate this. Find the most general antiderivative of. I'm going to give you two problems. F of x equals x to the 2/3, and f of x equals 3x to the 4 plus 8x. So I'd like you to pause the video and try these two. Okay, so for part A, I'm thinking this is just x raised to the n, where n happens to be 2/3. So we can use the rule that we have for x to the n, right? So we could try capital F of x equals x raised to something. Let me get another color here. X raised to some kind of power. And then it's divided by, it's usually divided by that same number, right? Whatever that power is. And then we have a plus c at the end. So all we have to do is take this and increase it by 1. So when you increase this by 1, you get 5/3. Put that in both places. But now I'm dividing by 5/3, so I would rather multiply by 3/5. And that's a good answer. By the way, let's check this. What's the derivative of 3/5 to x to the 5/3 plus c, where c is a constant? I'm checking the answer. You would bring the 5/3 down out front. The 5/3 would get multiplied by the 3/5. That's already there. You would decrease the exponent by 1. So it would decrease 1 less than this is 2/3. The derivative of a constant is 0. So there's like a plus 0. I'm not even going to write that. 5/3 and 3/5 cancel each other. And yes, it does check out. So that's just a little bit of scratch work for checking the answer. A little check mark. Okay, so part B. We could say capital F of x equals, and then just do like an antiderivative of each piece. The 3 is going to stay, and then it's going to be times x to the 5th over 5. The 8 is going to stay. Oh, how do we do an antiderivative of just x? We haven't really set a rule for that, but I'd like you to think of this as, isn't this kind of like x to the 1? So we could use that rule that says you raise the exponent by 1, and you also divide by that same number. You're thinking there should be a plus c at the end of this, right? But I told you, sometimes I'm not going to put the plus c when we're in the middle of a problem and we still have simplifying to do. I'm just going to make sure that the plus c shows up in the final answer. So final answer is simplified, and now I'm putting the plus c. Looks good. Looks good. And if you want to, you can check this answer. Take the derivative of this answer, and it should equal the original function. In fact, I think you can also do that mentally. Like you could just quickly in your head figure out the derivative of this. I see that we're going to get 8x. It looks like everything works. All right, so I have a definition for you, and this is going to be a new term for us, like a new word that we need to define, but it's also going to be a new notation. So we use the notation. It's a new symbol for us. It looks like this. And this is called the indefinite integral of f to represent the family of all antiderivatives of f of x. This is it. This is the sort of abbreviation that I've been talking about when we've been saying find the most general antiderivative of. We can now write it with this symbol. We can write it with this notation because it's the family of all antiderivatives. So in fact, I've kind of tricked you all along. What we've been doing this entire lesson have been integrals. We just weren't using that word yet. Now we have this word, the indefinite integral. Oh, it says indefinite, so it seems like maybe this is sort of hinting at the fact that there's going to be another type of integral that we'll talk about later. So yeah, indefinite integral is the one that we're talking about now. So here, some quick examples. How about the two problems that we just did? I'm going to write it with this new notation. We could say that the indefinite integral of x to the 2/3. There's a dx in this notation. Okay, so we'll write that. We found that it equals 3/5 x to the 5/3 plus c. We also did this problem above, 3x to the 4th plus 8x, and there's a dx in the notation. And we found the answer, 3/5 x to the 5th plus 4x squared plus c. So this is just a new way of writing the problems that we've already been doing. Here's the function that we want to find the most general antiderivative of, and here's the answer. How about this? I'll give you one to try. It's the same type of problem that we've been doing, but I'm writing it with this new notation. I would like you to find the indefinite integral of 3x to the 100 dx. So give that a try. Pause the video if you'd like. All right, so what you should find is 3 times, what do we do for x to the 100? We do x to the 101 divided by 101 plus c. I guess we could write this as like 3x to the 101, 3x to the 101 over 101. Maybe write it like that. You can still check your answer, by the way. Take the derivative of your answer. We'll do it. I'm going to take the derivative of my answer, the entire thing, like the plus c and everything. And yeah, derivative of this, it looks like the 101 would come down out front. It would cancel with the 101 on the bottom. I'd get a 3x to the 100. So everything checks out. So we are talking about antiderivatives. We're finding the family of all antiderivatives, also known as the most general antiderivative, also known as the indefinite integral, which is written in this way. By the way, we call this the integral symbol. Just call it the integral symbol. And yeah, we use the by the way, the dx part of it indicates that we are considering antiderivatives with respect to the variable x. All right, so the dx is there kind of for two reasons. One is it tells us what the variable is. Now, there's only one variable in this expression anyway, so I think we would probably see that we're looking at this indefinite integral. It says x to the 100, and you would probably say, you know, x seems like it is the variable. But you know that when we did derivatives earlier in the semester, sometimes we would have like a ddx. Sometimes we would have a ddt, you know, a derivative with respect to t or a derivative with respect to something else. So this is there to make it clear what the variable is. The other reason why it's there is it kind of tells us that the expression is over, like it's done with. It's sort of like the integral symbol begins the task of, you know, telling us that we are looking for the indefinite integral of what follows. And then the dx is kind of like a punctuation mark. It's kind of like we're done. So we want to find the indefinite integral of 3x to the 100, period. You could think of it like that. Because there might be stuff after this. So this tells us that it's done. Now, I'd like to tell you some rules. Oh, by the way, I guess I'll say this off to the side. The process of finding an indefinite integral sometimes called integrating the function. You know that when we were finding the derivative, we would often call it differentiating the function. So we could call this integrating the function. And in fact, if we are talking about this topic overall, we might refer to the topic as integration. This is integration that we're talking about. All right, so some rules for integration or for integrating functions. These are going to be the antiderivative rules that we said earlier, but I'm going to write them with this new notation. So here's a rule. If you have a times f of x dx, you can pull the constant out of the integral symbol. That's for any constant a. And this is actually the same rule that we said earlier. I think earlier I wrote it out as a sentence. It had a bunch of words. And this is a more concise way of doing it because we have this new notation with this new symbol. So that's kind of like in the problems that we've solved. If there was, there was an 8 out front, the 8 was still there after we integrated. Or I guess that 3x to the 100, the 3 was still there after we integrated. It's like we pulled the 3 out. Another rule is the indefinite integral of f of x plus g of x is equal to you can split this up basically. This is like saying the family of all antiderivatives of f of x plus g of x is equal to the family of all antiderivatives of f of x plus the family of all antiderivatives of g of x. So that makes sense. And we said that earlier as a sentence. Now we're writing it out with this notation. Here's one that we said earlier. The indefinite integral of x to the n. We had that general rule for this, and it was x to the n plus 1 over n plus 1 plus c. And this is true for any n besides -1. What about 1 over x? We had a rule for this. The family of all antiderivatives of this, ln absolute value of x plus c. How about e to the x dx? We said this earlier was e to the x plus c. Over here, how about for sine x, we found negative cosine x plus c, and a rule for the indefinite integral of cosine x dx is sine x plus c. You have to be a little careful with pluses and minuses when you're talking about sine and cosine, right? Because you know that when we take derivatives of them, we always had to think about like which one is positive and which one is negative, but this time it's kind of reversed. The indefinite integral of sine x now has a minus sign in front of the answer. And the indefinite integral of cosine x does not have a minus sign in the answer. So it seems reversed from what we're used to, but that's because we're doing antiderivatives. So it makes sense that it's reversed. This is a good little summary of rules that we have on here. And this, we can already answer a lot of problems just based on what you see here. Of course, there's still going to be more rules. We want to figure out how to find indefinite integrals for lots of different functions. And we also want to see some applications, what is all of this good for? I mentioned something at the beginning of this lesson about velocity and distance. Maybe we'll see some problems involving that. All right, so we still have some more to cover. We're not finished yet, but this is turning out to be kind of a longer section, so I just thought maybe we would take a little break here. Remember, it's always good when you're in front of the computer all the time. It's always good to take a break, give your eyes a rest, get up and stretch, get some water. So now's a good point to do all that. We're talking about antiderivatives. We learned what that is. And we learned about the most general antiderivative. It basically gets a plus c added to it, plus any real number. And now we have this new notation and a new word, right? We're calling it the indefinite integral, but it's still the same thing we were talking about earlier. It's the family of all antiderivatives, or the most general one. So it's, an antiderivative with plus c attached to it. You might be thinking, can we kind of take all of our old derivative rules and just somehow work them in reverse? Like, right? reverse kind of sounds like the word inverse. It feels like we're doing the inverse of the derivative if we're doing the opposite. So we're able to do that for a lot of things. Like we're able to think of, that's how we came up with indefinite integral for sine and cosine. It's by thinking about derivative rules in reverse. But then you might start to get a little concerned, like, okay, but what about the product rule and the chain rule and the quotient rule and all that? Is there like a way to do those in reverse? And the answer is that's why this topic is going to take several lessons, and that's why there's more to it than just this. But in this lesson, we're not worrying about those things yet. But yeah, we're gonna get to some of those things in the future. All right, so let's get back to where we were. Just thought we should take a little break there. Okay, so these are some of the rules that we were just talking about, and I'd like you to do some example problems. I think, you know what? I'll put a few problems here, and then I'll do the first one, and I'll ask you to do the rest. I'm going to use the word find. You know, sometimes we'll use the word compute, sometimes we'll use the word integrate, but we want to find out what all of these equal. So like I said, I'll do the first one. For t cubed plus 6t squared minus 1 dt. And then there's going to be a part c and d over here. All right, this last one is probably the toughest. So I'll do the first one for us. I'll just give you a chance in case you're writing these down. So here's the idea. With this new notation that we've been using for the indefinite integral, we could say, sometimes you could just call it the integral and leave out the word indefinite, and we understand we're talking about that type of integral. All right, what do we do? So we can pull the 9 out. We have that rule that says you can pull the 9 out, and now it looks like this. And you could think of the square root of x as x to the 1/2, and you could apply that rule that we did earlier. So you get 9 times, I guess, x to the 3/2 over 3/2. Now, it feels like there should be a plus c, but I know that I'm still working on simplifying this, so I'm going to wait and just put the plus c at the very end. How about instead of dividing by 3/2, we multiply by 2/3? I like that better. And now 9 times 2/3 is 6, so we could write 6x to the 3/2, and I'm going to make sure that my final answer has plus c. And that's a good answer. All right, so now I'd like you to pause the video and try the other 3 problems. So part B has a different variable. Instead of the variable x, it has the variable t. That's why it has a dt. It's just indicating that t is the variable. And other than that, we just do this like the usual rules that we've been using. So here's the problem. I'm writing it again. And you could split this up into the integral of each part. We could have a minus here, 1 dt. And maybe you don't need to write as much as I'm writing for this one, but it's kind of new to us, so I thought I would write all these steps. You could pull the 4 out, you could pull the 6 out. Ooh, I actually missed a dt here. Make sure you write all those integral symbols and all the dx's or dt's. I was missing a dt, so I just filled it in. So that should be there. All right, pull out the 6, t squared dt. Do we pull the 1 out? I guess that's a question. 1 is a constant. Do you think you pull it out front? The answer is you can. It's okay to pull the 1 out. we could leave it in or pull it out. So you could actually say 1 integral dt. That's okay. Sometimes you'll see it written that way. It means the same thing as what I wrote. Okay, so now I will finally deal with these integral symbols. So we know that for t cubed, we need to go t to the 4th over 4. For t squared, I need to go t to the 3 over 3. And then what do you think we need to do for 1? Well, I already had you pause the video and work on this. And I'm hoping that you found that this should be t, because the derivative of t would be 1. So an antiderivative of 1 would be t. And then we could simplify the answer and make this t to the 4th plus 2t cubed minus t. And in the final answer, we would like to put plus c to make sure that we're getting the family of all antiderivatives, not just one antiderivative, but all of them. At this point, I'm not going to do it, but I'm just going to remind you that you could check this answer. You could check this answer by taking the derivative of your answer and make sure it equals the original function. That's one of the nice things about math classes, is sometimes there are ways to check your answer so you know if it's right or wrong when you're handing it in. Oh, by the way, taking the derivative of this would be pretty quick, right? You could even just do it in your head. So a lot of times checking your answer is faster than finding the answer. You know, you go through all these steps to find it, but then you can check it really quick. For this one, 3 over x dx, well, here's what I'm thinking. I mean, that's the same as 3 times 1 over x, right? So we could actually pull the 3 out. So 3 ln absolute value of x plus c. Remember that the plus c should be there, and also remember the absolute value needs to be there for full credit. In order for this to be the best answer that it can be, it needs the absolute value. The reason I keep talking about making sure the plus c is there is because forgetting to put plus c is kind of notorious for calculus students losing, you know, 1 or 2 points here and there because you forgot to put plus c. So if the problem calls for it, make sure that it's there, because those points can add up. All right, this one, I said the last one looked like it might be the toughest, but we can do this. I mean, you might be looking at this and thinking, like, do we need something like the quotient rule, but in reverse? Well, we don't really need that. We don't need anything like that. I would say let's try to find a way to rewrite the problem in a more convenient way. And I think we did something like that earlier with one problem. Yeah, you could write it like this. Split it up. It's only one thing in the denominator, so we could split it up. And then maybe you even figure out that this equals x to the 1/2 plus x to the negative 1/2. And now we can just use the rule that we have for x to the n. So I think this is going to be the best way to do this one. So I get x to the 3/2 over 3/2. I know what we're going to do about that. And then x to the 1/2 over 1/2. I know what we're going to do about that. I'm going to rewrite this as 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. There's a couple of ways you could write this answer. I think the way that we got it looks good, but I'll show you a couple of other ways to write it. You could also say 2/3 x square root of x plus 2 square root of x. That's equal to what we had, right? Or if you wanted, you could actually pull 2/3 square root of x out and then get like x plus 3. Something like that if you want. Any of those are fine. Any of those three things. If you do something like this where you factor something out, just make sure that the plus c is all the way on the outside. The plus c should not be inside the parentheses. And the plus c should also not be under a square root symbol or anything like that. It should be just kind of floating out there by itself. Okay, so those were some good example problems. Hopefully you're getting more comfortable with doing these integrals and antiderivatives. We have something else to talk about for this section also, and that is if we're given more information, sometimes a problem only has one solution. In other words, we can solve for a specific value of c. Now, I'm going to underline the word if. If we're given more information. It's a certain type of problem. The problems that we've been doing so far, they didn't give us this extra information, so you'll see what I mean. But this new type of problem that we're going to talk about, it has a name, and this is called an initial value problem. I'm going to underline that, and it's sometimes abbreviated IVP. The way that these sometimes show up is as word problems. So I'm going to show you a couple of examples that are word problems. And I think it's also helpful to do that now because you'll start to see, maybe you'll start to see like some applications of what the integral is useful for or what antiderivatives are used for. So we need to be given a function that we're trying to find antiderivatives of. We also need more information. The more information is going to basically be what we call an initial value. So let me write a problem so that you can see what I mean. It's a word problem. For a company to produce X units of an item, the cost is f of x. The company knows that f prime of x is 0.3x squared plus 4x. Suppose the fixed cost of doing business is $1,200. In other words, it costs $1,200 when 0 items are produced. Find the cost function f of x. So I'm gonna walk us through this. This is new for us, but this is an example of an initial value problem. All right, so by the way, these lessons are for calculus, but I also sometimes teach a course in business calculus, and that's where I took this problem from. So this is a business application of antiderivatives, and a lot of times I'm more interested in sort of science and technology type of problems, but I thought it would be good to do a business problem. So, how do we find the cost function? I guess we know this seems like a lot of words just to basically say, here's f prime of x, and we want to find f of x. So we know that we're trying to think about antiderivative rules, right? But then there's this other stuff in there about $1,200. So we'll have to talk about that as that comes up. So here's what I'm thinking. I'm thinking that f of x is going to be an antiderivative of 0.3x squared plus 4x. So for antiderivatives, we've started thinking of them as the indefinite integral. Really, this would get me the family of all antiderivatives. So let's start here. Let's start with this. This is going to find the family of all antiderivatives, and then we're going to use the extra information to find the one specific function that is the answer. First of all, we could pull the 0.3 out. Let's split this all up. Let's pull out constants. There. That looks good. Okay, we know how to do these little integrals. We can integrate these. So 0.3 times x to the third over 3 plus 4 times x to the 2 over 2. I'm thinking that there should be a plus c here. And we could simplify this. 0.3 divided by 3 is 1/10. So 1/10 x to the third plus 2x squared plus c. We're not finished yet, but we're most of the way finished. So I think I have to move the problem off the screen to make room. But before I move it, let's just address that we haven't used the 1,200 yet. And it says it costs, like, this is supposed to be a cost function, and it's supposed to cost $1,200 when 0 items are produced. $1,200 when 0 items are produced. So we are given that the cost of producing 0 items is $1,200. That's what that sentence was saying, right? F of 0 is 1,200. And we're going to use that. Basically, we're going to put this into the answer that we found. We found f of x. The problem gave us f of 0. So let's say 1/10 0 cubed plus 2 0 squared plus c. All of that is supposed to equal 1,200. So I said before we did this problem that certain problems are going to let us solve for a specific value of c. And look what's happening here. We just got c equals 1,200 because that other stuff canceled away. So the cost function is the answer that we found above with the c value that we found. And I'm going to put a box around that. And that is one specific function instead of like a family of all functions. This is the one specific function that is the correct answer. Okay. And let's see. A couple of things that I'll say about this. That's the answer. I want to tell you that this piece of information that we were given, that's known as an initial value. So the way that we solve these types of problems, it usually involves integrating, right? Like finding the family of all antiderivatives. It has a plus c, and then we use the initial value that we were given. The initial value is called initial because usually you'll be given something like f of 0, so it's kind of like a starting value. But it turns out that it doesn't have to be 0 here. You could be given f of 1, you could be given f of 2, you could be given f of 3. The important thing is that you're given basically a function value, like you're given an input and an output. And that gives you something that you can put in, like we put 0 in, and something that's over here. So as long as you're given f of something equals something, it's considered an initial value problem. And you put it in after you've already integrated. And that helps you find what c is, and then you write your final answer. It's the answer we found above with the c value that we found. Now in this problem, this stuff canceled out, and c wound up being 1200. C is not always going to equal exactly what the problem said, but it worked out that way because these things canceled. I'll show you another one. Actually, before I show you another one, let's talk a little bit about motion. Like we talked about velocity and acceleration earlier in the course. So we're going to revisit that now. And I don't know if you remember, but back when we talked about position, velocity, and acceleration, at one point we drew a little diagram. And I'd like to revisit that. So position, velocity, and acceleration. So earlier in the semester, I drew this diagram where I said we get from position to velocity by taking the derivative. And then we get from velocity to acceleration by taking the derivative again. This time, well, I'll say derivative. Derivative here and derivative here. But this time we can also use what we've learned in this lesson about antiderivatives. Antiderivatives let us go in the opposite direction, right? So like if you know acceleration, you can find velocity. And if you know velocity, you can find position. And these are antiderivatives, which we've also learned the notation for thinking of them as an integral. So the diagram that we drew earlier in the semester, when we originally drew it, it was kind of a one-way street, and now we've turned this into a two-way street. So it's kind of like we're able to do this process forward or backwards. And that means that we can look at some word problems where maybe we're given some information about acceleration or velocity, or maybe even both of them, and then it could ask us a question about the position of an object or the location of an object. And yeah, we're going to use antiderivatives to answer that type of thing. And some of these might be initial value problems also. So I'll show you one. A hot air balloon ascending at a velocity of 12 feet per second is at a height 80 feet above the ground. When a package is dropped. The package falls. With an acceleration of negative 32 feet per second squared due to gravity. How long does it take for the package to reach the ground? All right, that's a long problem. Just give you a chance in case you're writing that. And we're about to leave that diagram behind, but we could take one last look at the diagram and make sure we have that in our notes, because we're going to use that to help solve this problem. So there were some letters that we used earlier in the semester, and I'm going to use them again when we talked about motion, like velocity, acceleration, that type of thing. We sometimes had S for position. It's also known as displacement. I mean, I guess in this problem, we could think of it as height, the height above the ground of the package, right? V for velocity, A for acceleration. And let's start with, what are we given? Are we given a function? Like, I don't see a function that we're given. I guess there's something about velocity, there's something about height, and there's something about acceleration. So it kind of gave us a little piece of information about all three. I'm going to start at the bottom of the diagram and work my way up. So I'm given acceleration. The acceleration can be thought of as a function of time. So let's write A of t. All of these can be thought of as a function of time. S of t, V of t, A of t. The function for acceleration just happens to be negative 32. That's the function. So it's a constant function. No matter what t value you put in, you just get negative 32. And that's because the acceleration is not changing, and that's because gravity is not changing. So it makes sense that gravity is a constant function. All right, so can we find v of t? Well, what would be an antiderivative or maybe an indefinite integral of negative 32? I think earlier we had a problem where we did an indefinite integral of 1, and we found that, let me find this. Where was it? Just show you this real quick. How about when we did this? We did an indefinite integral of 1 dt, and we said that it equaled t. So if I want to think about negative 32, an antiderivative of it would be negative 32t. And I'll put the plus c here because this could be plus any constant. You could check this, find the derivative of this, and it equals negative 32. Now, what else are we given? I said I was going to start at the bottom of the diagram and work my way up. We're given something about velocity, right? It says that the balloon is ascending at a velocity of 12 feet per second, and that would be at the moment when the package is dropped. So if t represents time, and it looks like time is going to be measured in seconds because this problem mentions seconds a couple of times, how about this? How about when the package is dropped, let's think of that as time 0. Like that's t equals 0. Maybe as soon as the package is dropped, somebody clicks a button on a stopwatch, and that's when we start timing. So I'm going to say that what we're given is the velocity at t equals 0 is 12. That was the hot air balloon was ascending, so the height was increasing. So this is a positive velocity. The package was moving with the hot air balloon until it was dropped. So when it's first dropped, the package actually had like an upward velocity, but then it starts falling. So this is an initial value that we can plug into v of t equals negative 32 t equals plus c. So let's put that in. So we get negative 32 times 0 plus c is supposed to equal 12. And it turns out that the 32 times 0 cancels. We get c equals 12. So the velocity function is the velocity function that we found above with the c value that we just found. That is the specific velocity function. Is this getting us where we want to go? Let's keep in mind, what are we trying to answer? It says, how long does it take for the package to reach the ground? Well, I feel like we should find something about the position of the object, right? Because we want to know when the position is 0 feet above the ground. Like that's going to be the moment when it hits the ground. So I'm working my way up the diagram. We went from acceleration to velocity. Let's try to find the position. If this is the velocity function, then the position function is an antiderivative of this. So we could write it as negative 32 t squared over t plus 12t plus c, where this c might be different from the previous c. If you'd like, you could label these like c1 and c2, but it's okay to use c for both of them. I think from the context, like from the way we've written this, I think we can kind of tell that this is a new c, but it's up to you. All right, so this equals negative 16 t squared plus 12t plus c. Do we have an initial value that we can put into this? Like an initial position value? Yeah, it said something about 80 feet, right? So I think that we were given s of 0 equals 80. So we'll put that in. Negative 16, 0 squared, plus 12 times 0. It's really nice when the initial value that you're given happens at 0, because that's when you tend to get a lot of things canceling. So look at that. Looks like c equals 80. So the position is s of t equals the thing we found above with the c value that we found. We're not finished yet, but I actually just want to highlight something here. I'm going to do this with an actual highlighter. So I feel like up here we have the acceleration function. Over here we have the velocity function. And over here we have the position function. And the thing that I wanted to point out to you, well, first of all, you could kind of check these, like find the derivative of the one on the bottom. Derivative of s is going to equal v. The derivative of v is going to equal a. So you can check those, make sure that checks out. I guess what I wanted to say is, now that we have these three functions, I feel like we could answer almost any question that you could possibly think of about this package. Like, you want to know its acceleration? I can tell you that. You want to know its velocity at a certain time? I can tell you that. You want to know its position at a certain time? I can tell you that. So having all three of these lets us answer a variety of questions. So if you're not sure what to do in a word problem, a good strategy might be to find all three of these and then take a second look at the problem. All right, so we have to move some of this away. I'm taking a second look at the problem, and what is it asking us? It says, how long does it take for the package to reach the ground? So we want a t value, right? It's like, how long does it take? So we want t equals something. My answer is going to be some number of seconds. I'm going to say that it hits the ground is basically when is s of t equal to 0? When is the height above the ground equal to 0? That would be the moment of impact. So we could take the function that we found, negative 16 t squared plus 12t plus 80, set it equal to 0, and solve for t. That's what this question wants us to do. And that's because it said, how long does it take to reach the ground? A different problem might ask us to do something else. So yeah, for this one, I'm setting the position equal to 0 and solving for t. First thing I'm going to do is divide both sides by 4. I think that makes this a little bit simpler. So it's a little bit better. Does this factor, though? Does this factor? Well, unfortunately, it turns out that this does not factor nicely. It doesn't factor into any kind of integers. So I'm going to use the quadratic formula. I mean, I think this semester we've had most things tend to factor, but you should be ready to use the quadratic formula just in case you can't factor it, because it's a quadratic and we could still solve this way. Quadratic formula has a plus or a minus sign, so I think we're getting 2 answers. Let's keep going with this and see what we get. All the stuff under the square root you could simplify. So I get minus 3 plus or minus the square root of 329. That's kind of a weird number to take the square root of, over minus 8. All right, how about this? Let's write this as how about we split this up? Let's have this part over 8 and this part over 8. So 3/8 plus 1/8 square root 329 and 3/8 minus 1/8 square root 329. So are these both answers? No, not really. I mean, because, we have a package falling. It's going to hit the ground at one time. It's not going to hit the ground twice. I mean, there's nothing in here that would suggest that it's bouncing or anything like that. So it hits the ground at one of these times. The trick is to notice that this is something positive plus something positive. So overall, this is a positive number. Is this one positive or negative? 3/8 minus 1/8 of the square root of 329. It's kind of hard to figure out what the square root of 329 is by hand. I guess we could say square root of 100 is 10. You could work from there to figure out that square root of 329. Let's do some scratch work. I'm trying to convince you that this number must be negative, but how can we see that without a calculator if we don't know what the square root of 329 is? So maybe we say, I know the square root of 400. You could use some square roots that Maybe like the square root of 169 is 13. etc. So what's going to wind up happening here is this equals 3/8 minus 1/8 times, this is scratch work, so it's okay if I'm being messy with it. Can you see that the number that goes here must be a pretty large number? So 3/8 minus 1/8 times something that's larger than 13. Like, this is going to wind up getting us a negative number. There can only be one answer, and I don't think that the package can hit the ground before it was dropped. The package has to hit the ground at a time after it was dropped. So this is going to be the answer. 3/8 plus 1/8 square root 329 seconds. It takes that many seconds to hit the ground. So we kind of like tossed out the negative answer, because it can't hit the ground before it was dropped. All right, so in a word problem, if you get two answers, sometimes you have to figure out which answer makes sense. By the way, I'll tell you, just as kind of an afterthought, like we did finish the problem, but I'm going to tell you that this is approximately 2.64, and that this one over here was approximately negative 1.89. So anyway, yeah, about 2.6 seconds after it's dropped, the package hits the ground. All right, that was a long problem. You could review what we did and remember the things that I highlighted earlier is, we basically found the acceleration function, velocity function, and the position function. We were doing these as initial value problems, like putting in the given info to help us find C. And then ultimately we had to figure out what question is it really asking, and we said, all right, it's really asking me when is S of t equal to 0. We set it equal to 0 and solved. Unfortunately, it didn't factor nicely, but we were able to get the answer anyway. All right, I've got a problem for you to try. I know this has been a really long section, but this is kind of the big section because it introduces us to things that we're going to be talking about for the rest of the semester. This, I think, is going to be the last problem that we do for this lesson. A driver applies the brakes on a car moving at 45 miles per hour. On a straight road, and the brakes cause a constant deceleration of 22 feet per second squared. How many seconds will it take for the car to stop? Before you, I'm going to have you try this, but before you try this, I have a hint to give you. Hint: convert 45 miles per hour into feet per second before solving this. Okay, because it gave us, I want to say that this problem gave us one of the distances is in miles and the other one is in feet. One of the times is in hours and the other time is in seconds. So these seem incompatible with each other. So in order to make them compatible with each other, we have to convert one of them into the other. So I'll let you figure out how to convert those units. And now's a good time for you to pause the video and give this a try. All right, so this seems like a very practical problem. I mean, somebody's driving on a road and they hit the brakes, and we need to know how many seconds it'll take for the car to stop, right? So first of all, following the hint, it said to convert. So 45 miles per hour. Well, you can figure out how many seconds there are in an hour, right? Because it would be 60 times 60. So 45 miles per hour is going to be 45 times, there are 5,280 feet in a mile, and there are 3,600 seconds in an hour. Oh, I guess 45 goes into 3,600, doesn't it? So I guess I did that division, and then I got a number, and then I divided that into 5,280, and I got 66 feet per second. So that's the conversion that I wanted to do. So now when we work with the 45 miles per hour, I'm going to work with it as 66. I'm going to say that we were given that the acceleration function is negative 22. You know, in the previous problem that we did, we had an acceleration function of negative 32. That was like a falling package with, falling due to gravity. I'm using negative here. And the reason I'm using negative is because it says deceleration. So that can be a little bit sneaky, but it did not say that the acceleration is 22. It said there's a deceleration of 22. So it's the car is slowing down, right? So the car is slowing down. The acceleration is negative. I guess the rate at which the velocity is changing is a negative rate. So can we figure out the velocity function from this, v of t? Yeah, you do it like this, right? You do negative 22t plus c. And then I look to see, is there an initial value that I'm given so that I could maybe find out what c is. Well, at t equals 0, the moment that the brakes are applied, the velocity was 66 feet per second. So yeah, we're basically given v of 0 equals 66, and I'm going to put that into negative 22 times 0 plus c equals 66. And this cancels, and I wind up with c equals 66. The velocity function is v of t equals negative 22t plus 66. Oh, you know what? In the previous problem, I highlighted the acceleration and velocity and position functions, so I think I'll do that here. There's the acceleration, there's the velocity. That's what we have so far. Now, before we go any further, let's take another look at the question. And what is it really asking us? It says, how many seconds will it take for the car to stop? That seems like it's a question about velocity, doesn't it? I wanted you to notice that the car stops when its velocity equals 0. That's what it means to stop, right? Your velocity is 0. So we can just take the velocity function and set it equal to 0 this time. You don't need the position function, because this question is about how long does it take to stop. So yeah, we could solve this. Negative 22t equals 66. T equals 3 seconds. It takes 3 seconds for this car to stop. It takes 3 seconds before the velocity becomes 0. So I think this problem was a little bit shorter than the hot air balloon problem. I think that the tricky parts of this, I guess at the beginning you had to convert the 45 miles per hour to feet per second. So there was that part. And then I guess another little tricky thing was noticing that the acceleration was going to be negative because it used the word deceleration. So that had to be a negative 22. And then the rest of it is kind of like the previous problem. All right, so take a deep breath. I think that we are about ready to wrap this up. All right, so we made it through. This was probably the longest lesson of the semester. I haven't really like assembled the video yet to see how long it is, but I think this is probably the longest one. So we made it through. We learned a lot, and it was such a long lesson because this is the topic that we're going to be talking about for the rest of the semester. Every lesson we do for the rest of the semester is going to have to do with antiderivatives and integrals. So we wanted to make sure that we did like a very thorough introduction to this whole topic. And also, the reason this wound up pretty long is because I had some extra problems and I worked in all the extra problems that I had. So you saw more problems than I usually show, and I hope that that helped. So we made it, and that's it for now. So take care, and I'll see you next time.